So in this video we're going to look at a model for electrical flow using matrices. So what we have here is an image of an electrical circuit, and in this diagram we have three different things showing up. We have I's. Here's I sub 1, I sub 2, and I sub 3, and those represent currents, and currents are always going to be measured in amps. So this is actually, current is just a measure of the electrons per unit time moving through the electrical system. If I were to draw an analogy to an irrigation system, which we're pretty familiar with here in the valley, the current would be kind of equivalent to the water flow rate through the piping in an irrigation system. So think of electrons flowing through pipes, but they're moving through the electrical wires. So these are measured in amps. I sub 1 amps, I sub 2 amps, I sub 3 amps. And so the first big idea, before we talk about the other pieces, the first big idea is that the current, the flow of electrons per unit time into a junction, so junctions are these places here where we can think of those as where the wires are coming together. So the flow rate of electrons per unit time into a junction has to equal the flow rate coming out of the junction. You can't have more electrons coming out than what are going in, and if they go in, they have to come out. So for example, this junction right here, what I would say is that there are I sub 1 amps or I sub 1 electrons per unit time coming into that junction, and the number of electrons coming in have to equal the number of electrons exiting, and there are I sub 2 amps plus I sub 3 amps exiting that junction. So that junction gives us this equation. I sub 1 has to equal I sub 2 plus I sub 3, and we can manipulate this by subtracting I sub 2 and I sub 3 from both sides. We can manipulate this so that we get the equation I sub 1 minus I sub 2 minus I sub 3 is equal to 0. So here's an equation. And notice there's three unknowns. What we're going to want to solve in this is for the current, and I sub 1's represent the current. The current, or electrons per unit time in amps, that are moving through each branch of this electrical network. So we really have three unknowns that need to be solved for. Each current goes with a specific wire. So if you think about this as a junction of wires, I sub 2 represents the current through this wire. I sub 1 represents the current starting here at this junction, moving all along this wire. So everywhere this is I sub 1. And I sub 3 represents the current moving through this particular wire. So the junctions, you want to think of the junctions as breaking the diagram up into distinct wires. That's one way to think about it. I have another junction here, but what I want to notice is I'll get the same equation from this junction, because this says I have I sub 2 amps plus I sub 3 amps coming into the junction and I sub 1 amps exiting the junction. So I would wind up getting I sub 2 plus I sub 3 equals I sub 1, which is the same equation I got from this first junction. So I want to move, so that means that I've gotten all the equations I can get from Kirchhoff's law 1, which says the current flowing into a junction has to equal the current flowing out. If the diagram is a little more extensive, you may get more than one equation from Kirchhoff's law number 1. It just depends on how many junctions there are and how they are interconnected. So the next piece is this. It says paths. So a path is any closed path in the system. So here's some examples of it's actually three closed paths in the system. So for example, if we take it from the perspective of this junction, you could start from that junction, flow outwards, and that would create a path right there. If I start here, I could flow this way and move along and close up and have a closed path there, or I could start here and flow along the entire outer wiring. Usually when I look for paths, I look for paths where the arrows are pointing in the same direction. So for example, this path, here's a path I would not choose to use if it were me. Here the arrow's pointing, I'm moving in the direction of motion, and if I continue moving clockwise back towards this, I see that I'm moving opposed to the direction of flow. I usually avoid those. So the idea is that if you take the product of I times R, and I is the current, and R is resistance, and these symbols right here represent resistance. These are your R's, and resistance is measured in ohms. A lot of times you'll just see this with the symbol for ohm, which is this. So that would be another way of saying 1 ohm. These represent resistances. These are represented with R's. And the idea is that if you take a flow, I, and multiply it by R, the result is a voltage. And on a closed circuit, the sum of the voltages that you get from doing the current times resistance has to add up to the voltage you get from the source. This is like an irrigation system. This would be like the pump. In this case, it's an electrical system. This could be like a battery, a 33 volt battery. Right here, could look at this as being an 8 volt battery. So here's how this works. Let's use this closed circuit right here. So as you move along that closed circuit, this flow hits this 1 ohm resistance. So you get 1 times I sub 2, the product of current times resistance is volts. So if you do 1 ohm times I sub 2 amps, you get an output that's in volts. This output here is in volts. And if I continue along this closed path here, I have I sub 1, my current I sub 1 hitting 6 ohms resistance. So 6 ohms times I sub 1 amps is going to give me a result that is in volts. And as I sub 1, my current moves along and hits this resistance, 2 ohms times I sub 1 amps is going to be 2 I sub 1 volts. And what Kirchhoff's law number 2 says is that the sum of these IR voltages along a closed circuit has to add up to the voltage being produced by all of the batteries or electron sources along the circuit. They don't have to be batteries, but you could think of them as being batteries. So for example, this one I get 6 I sub 1 volts plus 2 I sub 1 volts plus 1 I sub 2 volts. So 6 I sub 1 plus 2 I sub 1 is 8 I sub 1 volts plus I sub 2 times 1 gives me I sub 2 volts here. So 8 I sub 1 volts plus I sub 1 volts has to add up to the 33 volts being produced by the electron source on that particular circuit. And then if I look at the outer larger circuit, which I like because the arrows along this outer circuit are all moving the same direction, you see here you have I sub 3 amps hitting a resistance of 3 ohms. So we get 3 ohms times I sub 3 amps gives us a measurement in volts. And as we move along, we're going to hit this one we already calculated. 6 ohms times I sub 1 amps equals 6 I sub 1 volts plus 2 I sub 1 volts from this resistor right here. And those are the only place where I have resistors along this circuit. And so we get, again, the sum of the volts from the IR terms. 6 I sub 1 plus 2 I sub 1 is 8 I sub 1 plus, over here we got an IR term, 3 times I sub 3 ohms times I sub 3 amps is 3 I sub 3 volts. So 3 I sub 3 volts has to add up to the voltage along the closed circuit coming to you from the electron sources or the batteries. So here's an 8 volt battery along this outer circuit plus a 33 volt battery along this outer circuit. So we get 33 volts plus 8 volts is 41 volts. And now I have 1, 2, 3 equations for my 3 unknowns, so I can set up a matrix that I can solve. Say, hey, I'm going to create a matrix from this system of 3 equations. I'm going to have an I sub 1 amps column, an I sub 2 amps column, an I sub 3 amps column, and my constant column. So here I just read off my coefficients. 1 I sub 1 minus 1 I sub 2 minus 1 I sub 3 equals, here's my augmented matrix, equals 0. Here I have 8 I sub 1s, 1 I sub 2, there are no I sub 3s, and I have 33 volts. And here I have 8 I sub 1 plus there's no I sub 2s plus 3 I sub 3s equals the 41 volts. So there's my augmented matrix. And now we need to put that into reduced row echelon form. So let's keep those changes, slide that over, bring GeoGebra open, and we're going to need to put GeoGebra into, under view, go into that spreadsheet view again. We won't need the graphics window. And let's go ahead and move our matrix into the spreadsheet. So the first row is 1, -1, -1, 0. So 1 tab, 1 tab, whoops, sorry, 1 tab, -1 tab, -1 tab, 0, enter. The second row is 8 tab, 1 tab, 0 tab, 33 volts, enter. And we have 8 tab, 0 tab, 3 tab, 41 volts, enter. And then once we've done that, we can highlight our matrix, right click to get the context menu, create our matrix. I'm going to rename my matrix by right clicking. I'm going to name it E for my electrical circuit. I bumped cap locks on, so okay. And now I'm done with the spreadsheet view. I'm going to get rid of it. And I'm going to open my computer algebra system. And now GeoGebra is not responding, so I hope I don't have to reshoot the entire thing. Oh, that's going to be disheartening. Oh, there we go. Reduced row echelon form, type that into the menu. Reduced row echelon form of our matrix E, and then hit enter. And then we can interpret the results. Once we've done that, and let me bring open my ink tool so I can annotate. So what we want to remember is that this was an I sub 1 column, an I sub 2 column, an I sub 3 column. So this is I sub 1, 1 I sub 1 equals, and this is the current, so it's measured in amps, equals 4 amps. And here I get 1 I sub 2 is equal to 1 amp as my measure of electron flow. And here I have 1 I sub 3 is equal to 3 amps. So again, we want to keep the units on these, and that is the electron flow measured in amps through each of the branches in that electrical circuit.